hot inside. Or is it good? Do you want to get it colder? Yes? For me, it's super nice like that, but colder? Okay. So I will decrease the air conditioner.
Okay. Okay, can I start? Okay, so let's continue. Now for the second part of my lectures, by 3 lectures. So now we are going to switch gears a little bit. So we are going to discuss these networks, but now based on these atomic collective states. And one thing that is important to realize, and let's see if I can clarify throughout this talk, is that you can also have different ways to enhance the interaction of a material system with light, and this other way is to use these collective states. And I will start to discuss this at this lecture, this kind of state, but maybe next lecture I can come back to that, because I mean this is also connected with how you can approach quantum entanglement from natural phenomena, for natural light scattering. For much of what we are going to use in this lecture today, we are going to discuss Raman scattering. Okay, so actually, it's a pathway also for quantum information nowadays to be able to recognize, I mean, where are the quantum correlation in very common phenomena. Okay, and then we are going to explore here is everything actually is related to Raman scattering. Every time you have some Raman scattering, you should have some quantum correlations behind it. Maybe next lecture, I'll discuss a little bit about Rayleigh scattering, which you can also approach the quantum correlation in Rayleigh scattering. But I just want you to remember, even though we are going to discuss new experiments and new phenomena, a part of this process is related with systems that are simpler, they are more accessible, but you need to know where to look at. Okay. But before that, another thing that we didn't discuss yet for communications, that we didn't actually consider too much in details how the photons will go from one side to another, okay, and how distant that could be. All experiments that I discussed with all the impressive experimental development, they were all local experiments over an optical table, okay? We didn't connect distant objects. And then the development that I'm going to discuss here is very much connected on how to do quantum communication in practice. And one of the first problems that you have is the problem how you are going to deal with losses in optical fiber. Then, for example, if you want to do communication over long distance in a usual telecommunication system, when you pass through an optical fiber, your pulse decrease the size, but then you include a repeater in the pathway. This repeater just boosts the pulse, and then you can go through another piece of fiber, okay? And then you can just put repeaters on the pathway, and in this way you can really propagate your system for a very long distance. But this is a problem for any quantum network, okay? Because a quantum state cannot be amplified, okay? So, and this problem leads to the fact that the current quantum cryptography technology is typically limited to around 100 kilometers. You have experiments with longer distance, but that's roughly the order of magnitude that you are really restricted to. When I say that a quantum state cannot be amplified, what I'm talking about is what is called a no-cloning theorem. This theorem is actually very simple, okay? It's just say the following. I mean, let's say that you have a perfect cloning machine, okay? And this cloning machine would work like this. You have the state of your machine before interacting with a system S in a certain state. And the machine would evolve to a different state after interaction with the system, but the system would be double. You'd end up in a product state between that would be 2 copies of the first state. That would be your cloning or amplifying machine. And that's fine, but look at what would happen with this cloning machine if this machine is going to clone vertical and polarization and horizontal states of light, for example. So you want to just make a clone of a vertical photon, okay? Then you have this vertical, 2 vertical photons here. You can do a cloning of a horizontal photon, and then you would have this double, these 2 horizontal photons here. You can have different states of the machine after cloning one of these states, but let's assume that, I mean, now you act on a superposition of vertical and horizontal, okay? Then this is just basic quantum mechanics. I mean, if you apply this cloning operator to the system, so you can distribute the action over vertical and horizontal states, and you end up with something like this. And the problem is that in the ideal case, this machine would be in the same state after cloning both. That would be the best situation possible, and then you factor this out, but you end up with this kind of state. And this is not a product of 2 states that are like this, you see? So actually, this clone machine did not succeed to clone anything, okay? It just generated a state, but this state is very different from what would be the cloned state, which would be the product of 2 states exactly like this. This is just to say that the problem that you don't have a cloning machine, this just comes from the problem that your quantum mechanics obey linear optics rules, okay? So this is a very basic problem. Actually, this is an article in Nature, and this is the whole article, actually. This solved a long-standing issue, because since the beginning of quantum mechanics, the problem of stimulated emission, so you can have an atom in an excited state, comes a photon, and the photon can induce a decay of the atom with the emission of a photon exactly in the same state of the one that was exciting the atom. And this looks like a cloning, okay? But I think this very simple article clarified the situation. You can clone any photonic state, okay? But you cannot clone an arbitrary state. That's the big difference, okay? So sometimes you hear things like, oh, so classically, you have a repeater. You can amplify a classical signal, but you cannot amplify a quantum signal. You have to be careful on this. Everything that you can do classically, of course, you can do quantum mechanically. So if you know what your system is, what's your state, you can clone it, okay? You cannot clone it is just an arbitrary state. So what's the difference mean? Let's say that your state is a triangle, and classically you just make copies of that. And then another state is a square or a cube, and then you make many copies of this cube. The problem here is that for quantum mechanics, you will receive a box with some object in it, and then you say, okay, how can you clone this object that you don't know? Classically, you just open the box, look at the object, and make a copy, okay? Quantum mechanics, that's what you cannot do, okay? So that's just to clear up. So the problem is arbitrary states. So, and then you cannot, because many of the interesting things to do with quantum communication channel is related with arbitrary states, okay? And then if you cannot make a copy of this arbitrary state, effectively, you have a limitation in the distance, okay? So this is the moral of the story. I already anticipate that. Okay, so you cannot clone this arbitrary state thing. And before I get into how we can solve that in the context of this, this quantum networks with atomic ensembles, let's start with a more simple entangled state. Let's start with photon pairs that we get from a nonlinear optical crystal. Okay. So let's say that you have some nonlinear crystal with that generate pairs of photons by spontaneous parametric down conversion, this SPDC process. And then you can come with a pump pulse with a certain polarization. And as a result, the energy of this pulse is split in two parts. Okay? And then it emits two photons with orthogonal polarizations. Okay. So how can we use that to build an entangled photon pair like this? Okay, so this is a Bell state like the one that I discussed in my previous lecture. Okay, but this now would be a Bell state between two photons, and you can have one photon with a polarization in the x direction, the other in the y direction, or vice versa. So what we can do is we can use something like this. So this is the same system here that these two sides. I'm just pumping it with one polarization, here with a polarization which is vertical. I mean, vertical mean outside of the screen, okay? And it enters, and it just it's reflected in this PBS, goes through this crystal, and then you have the two photons. One comes here, and the other comes in this direction. Or you can come with a horizontal pumping beam, and then it goes in the opposite direction. But you also have photons that comes out in these two situations. You see that if you use a pump beam in 45 degree, and then you excite both systems simultaneously, you would have an output one with photons with vertical or horizontal polarization, and the output two would have exactly the opposite one. But you would never know which of the situations you are in. And that's how you generate this kind of state. In practice, that would be maybe the most straightforward way to generate this kind of state. And, okay, so we can do that. And if we can do that kind of state, we can also work with this kind of process that's called quantum teleportation. And that's what I would explain now a little bit. So the teleportation here comes from science fiction, really. But even though I think it's a good name, you see the reason here. So let's say that we start, okay, with an entangled photon pairs between sites 2 and 3. So Alice here is 2, and Bob is 3. So let's just consider two sites. Okay, 2 and 3. And the photons in site 2 and site 3, they are entangled, okay? And then you have a state like this. You see now I'm representing polarizations as just up and down. So up would be vertical and down like horizontal polarization. And this is then vertical polarization in site 2, horizontal polarization in site 3, and vice versa here. And look that I also produce a particular Bell state with this minus sign. No? Okay, let's say that Alice wants to transmit an arbitrary state, okay, to Bob. This arbitrary state would be this phi1, okay? So you have this state here would be system photon 1, so it would be this another party in your system. And so in the beginning, before you do anything, you have a product state. The whole state would be just the product of these two states. And once you do this product, you have something like this. You see that this product now depends on A and B, which is the amplitudes of probability for the state that is arbitrary. So from this point, we can actually change the basis just for Alice. Okay, so you can write the Alice state here, this 1, 2 state. You can write in terms of the Bell basis. Okay. And in terms of this new base, now using these states, you can rewrite the whole system like this. Okay, this is just rewriting this state in terms of the Bell basis for the particles, the photons, or this is general parts that are with Alice. Okay, so if Alice measures, her system in a Bell base, that is, if she does a measurement here, and the measurement, the output would be, okay, you can be in this state, PC12 minus, or PC12 plus, or Phi12 minus, or Phi12 plus. If she can identify which state, then she can send this information to Bob, and actually Bob can do a transformation, because all of these measurements result in a different projection in Bob. And after this projection, Bob can do a measurement to rebuild state Phi1, okay, this state here. And so this is a quite important result, because you see that in this way, actually you can transmit the state Phi1 that you don't know, which is, it's an arbitrary state. You can transmit this state to Bob. You cannot make a copy of it, because that's what's prohibited by the no cloning theorem, but you can transmit it through this process. And of course, the name teleportation comes from the fact that the state was never transferred physically from one place to the other. What you have before everything was just quantum entanglement, and you use the entanglement to actually transmit the state without this state ever really crossing the space between the two sides. Okay, so just to give an example, how can you do that with photons? Look, it's very different. You can build many systems in that Bell basis. I just mentioned in the morning that we can use like a cavity QED with 2 atoms. You can build a Bell base with the atom. The way that you measure this Bell states is completely different depending on the physical system. So I'm just illustrate now how we can measure that with photons. Okay. Okay, so you have this state here, these different states, 1, 2. And let's say that you come with photon 1. So now these physical systems are 2 photons. Photon 1 entering one side of a beam splitter, photon 2 on the other side, and then you have 2 outputs, A and B. Okay? So for a photon coming through the port 1 with a vertical polarization, it will transform after the beam splitter to this state. Okay? And for the photon 2, it will transform into this state. Okay, so this is more standard procedure. But then, well, let's come here. I think it's going to work now. Then let's say that you have a pair of photons is arrived at the beam splitter with the same polarization. Then it's just that we need to just operate with these 2 systems. This is just the product of these 2. And you will end up with this situation here. I'm going to come back to this later. This is also a particularly important system. If you enter a beam splitter with 2 photons that are indistinguishable, they are after the beam splitter, you cannot know from which what's the origin of this photon, from which side it entered. Once you have that, you see that all the 2 photons goes through one port A or just the port B. This is a particular important interference effect, but this is just the procedure. If you follow the procedure here, you end up in this situation. But let's say then that you enter with the other polarization, then you end up with a similar result. And if you come with cross polarizations, then you don't interfere, and you have now 4 terms for the output, and the same thing for the other situation with opposite polarizations. Okay, from that point, then we can start to build the outputs. For this input, for the input here, for Alice, with photon 1 and 2, this Bell state would project into this output, this state in the output. And each of the Bell states would project in different outputs. From these outputs, if you pay attention, there is only one of these Bell states that you have one photon going out in each of the outputs. All other Bell states, you have only, or all photons go to A, or all photons go to B. There is only one Bell state in the input where you end up with one photon A and another photon in B. That is, a coincidence measurement here would signal that you have this kind of state. Okay? So that's how the first experiment was done, first experiment in Zeilinger's group in 1997. So in this case, they created an entangled photon pairs using parametric Down conversion, exactly how I explained earlier. But they also created another photon, okay, in an arbitrary state, and then they combine this arbitrary, the state with this arbitrary photon with one of the photons of Alice, and then they did exactly this measurement with a beam splitter, okay? And then there is a 50% probability that the result will be this one. And of course, once you know that, this information is transmitted to Bob, and then Bob can do exactly that transformation, and then Bob can check what's the state of his photon here, and then can check the fidelity with the initially prepared state. And so it's not exactly teleportation I suggested originally, because it's a probabilistic teleportation, but it captures the idea. Other developments from that point on for quantum teleportation were deterministic measurements, like with coherent light beams in 1998, and also with ions in 2004. For ions, it's closer to what I discussed earlier with two atoms, for example. So all these realizations were deterministic. They could check the full Bell basis. But for this discrete number of photons, of just single photons in polarization state, then you have this limitation. This evolved later. Actually, it's not very difficult to see how you can increase for 50%, for example. I mean, you have this option, okay? But look at what's left also. You see this state here in A and B, you see that they have opposite polarizations. So if you, in the output A, you put a polarizing beam splitter in another detector. In B, you have a polarized beam splitter in another detector. If you have a coincidence in B or a coincidence in A, then you signal this other state here. So you can increase that pretty straightforwardly to 50% probability. But this other part here is more tricky to detect with the photons like this. Okay, but you can do teleportation. Okay, that's a tool that you have to use. And this was a very important development in the beginning of the 90s, because this basically means that, so you now know that the state cannot be cloned, but you can transfer the state to another system. And also, you create this new idea that one entangled pair of particles plus a classical communication channel, you can realize a faithful transmission of a qubit. And in a certain way, this causes a decoupling of the information into purely quantum and classical part. And then the entangled pairs can be used to transmit the quantum part. Okay? In the end, what you have here is that quantum entanglement as a basis of an engineer for quantum communication channels. That's why when I draw the quantum network, right in the beginning of this course, I draw a quantum network with channels that you can have a quantum entanglement through those channels. That's because quantum entanglement is a generic quantum communication channel, because you can have teleportation. Okay, then we can come back to this, to the idea, how can we build, okay, a quantum repeater now, okay? So we have a classical repeater, which you just generate copies of a state that you know what it is. But for a quantum repeater, now it means that we can have, for example, some entangled pairs of particles in two different sites. But you can have actually another pair connected, C, for example, with D, with B and C in the same site. And then we can do a Bell measurement here, resulting in the entanglement of A with D. So this procedure is exactly the same procedure that you do for teleportation. The thing is that if you do that procedure, but with two entangled pairs, what results is just entangled pairs in what's left. This means that particle A and particle D, they never interact, okay? But they can still be entangled through the entanglement between the intermediate particles. So that's called entanglement swapping, okay? And that's a very important concept, okay, because that allows to actually enhance, increase the length of this entangled state, in principle, at will, okay? So this is a tricky issue. Due to the no cloning theorem, you do have a limitation in the distance that you can connect. You can send, for example, a photon, and then to do, for example, cryptography between two sites. But these limitations for entangled systems, they are not. There is not really a physical boundary as strict. Okay? Because you can work to build this kind of networks of entangled state and then perform this kind of measurement to enlarge the distance between them. Okay? And in practice, actually, you end up requiring some kind of storage. That's where the atomic systems enters. And this is already the case for the cavity QED systems. Because the problem is that when you start to build a linear network like this of different systems, and you want to do that efficiently, there is only two ways to do. You can do that deterministically. Okay? Let's say that you have a process that will succeed for sure every time. That's the best way. Then you say, okay, I want to build this network now, and then you have the network. Or you can do it with memory. With memory, then you can build different portions of it probabilistically, but then you can store your state. And once you store other parts of state, and then once you have the whole network of entangled states in place, then you start to do the operations. Okay. So the scalability comes with memory in the case that you don't have some deterministic process. Okay, and then that's where this DLCZ protocol enters. That's where I worked for a while. And that was an important protocol because it basically proposed a way to use atomic ensembles and linear optics to do this quantum repeater architecture. Okay? This part of these authors are also involved with the quantum networks with cavity QED. So you have to understand this kind of work as a, let's say, hardware, is a more hardware-specific system. It's specific for certain capabilities, okay? So you have the cavity QED systems where you can do processing or you can do communication, but then you can also devise simpler systems to do some of the tasks, but not all tasks, okay? And that's the goal here. So what you have for this protocol, you have a source of photon pairs. These are not more parametric spontaneous emission for parametric down conversion. Okay, we are going to use something else here that I'm going to detail soon. But in the end, you are going to have photon pairs in the same way as you have in parametric down conversion. So we need to have a way to entangle distance ensembles, okay, using just beam splitter and the emission from these different ensembles. And also you need a way to do entanglement swapping, and in the end, some cryptography, okay? So look that the goal here in the end is to do cryptography, but actually the system, you can also do teleportation, can also do some other tasks. Okay, then how you can generate photon pairs here? So first you have some atomic vapor, which can be hot, but typically will be cold, okay? The cold atomic vapors are much easier to work with for this kind of system. And then you come with a right pulse on this vapor, and there is a probability that you will emit a photon. And together with the photon emission, you have a collective entangled state in the system that's stored in the system. Okay. After some time that the experimentalist determines, because it depends on the coherence time of your source, then you can come for reading pulse, and this stored collective state is mapped in a second photon. And these two photons are the ones that are entangled. Okay. And so this possibility to wait before you emit the second photon is what results in scalability once you have a complex process that you require many photons for them to perform that process, okay? So you can actually just store this state and then wait for another part of the system to store another state and then wait for another part of the system. In the end, you can read out everybody together. Okay, it's important. Time scales here are important as well. So the first proposal, the theoretical proposal is 2001. So this was done already in 2003. Okay, and I think this process it was really the development from there was really quickly because all the experimental techniques were already, I mean, dominated, let's say. And it's really a theoretical development, okay? The theoretical development is how can you see these collective states and how can you read out and what can you do with these collective states. This actually enters in an old subject that's I'm going to highlight now. So look, what do we need to do that, to have this system? You need to have an atomic ensemble with 3-level atoms, and you have these 2 ground states here. And we pump now all atoms for just one of the ground states. And our collective state is actually just a cylinder of atoms in the middle, for example, of a magneto-optical trap. So let's say that you have a spherical cloud here with your whole cold cloud. But actually, what you are detecting is a photon that would come from just a small cylinder here, okay? Your collective state will have the shape of this cylinder, the cylinder that you are collect the light from it. So typical numbers here are like 3 millimeters cylinders with 60 micrometers diameters and around 100,000 cesium atoms, or rubidium atoms, the atoms of your choice. And so when you come with a right field over the system, you just connect to this ground state with an excited state, and then you spontaneously emit a photon in field 1, okay? And the tricky thing is that once you emit this photon, okay, you know that to be able to emit this photon, you had to cause a transfer of one of the atoms from the G state to the S state. You see this photon here will come with a different polarization than the right field, and also with a different frequency. So this is spontaneous Raman process, okay? So in spontaneous Raman process, that's an inelastic scattering of light, so you necessarily have to change the energy state of your material system. And this change comes with this one atom being transferred. So one photon means one atom transfer. But you don't know which atom was transferring that cylinder, the whole cylinder. So this is the kind of collective atomic state that you generate, okay? So this kind of state was known for a long time already. This is a Dicke state, okay? So this kind of collective states was first theoretically analyzed in the 1950s, okay, connected with the problem of superradiance, okay? So you have, theoretically, if you have any spontaneous emission in an ensemble, you typically will generate this kind of state. But not necessarily are going to be able to use it. You have to know where to look and how to be able to use it. And actually, the recipe for that protocol, that the LCZ protocol, was how can you generate a collective state spontaneously in a way that you can use it to do quantum communication. So that was pretty important conceptually because super radiance has a lot of problems with interpretations of, is it really quantum? Because, or you have some semi-classical interpretations for it. And this kind of process, as proposed in the DLCZ protocol, it only works with the quantum interpretation of the problem, because we are going to use like the quantum properties of this kind of states to do many different stuff. So there is no semi-classical alternative for this kind of phenomena that I'm going to discuss. But this kind of state, they are ubiquitous. They appear in many situations if you try to do any first principles deductions using quantum mechanics to basically model your spontaneous emission process. So, in the end, you are going to end up with this entangled state in which you have some probability of having 0 photons in field 1 and 0 atoms transferred to S, or 1 photon in field 1 and 1 atom transfer, or 2 photons in field 1, 2 atoms transfer, and so on. Okay? So this kind of state, that's called a two-mode squeezed vacuum. That's exactly the kind of state in the number base that you generate in a parametric down conversion process. Okay? It always appears once you have any process that you scatter a photon, and then you leave some information in the system. So you imagine that you have an ensemble of light, and then you excite here with a laser, and then you detect a photon that came in this direction, okay? If you detect something in this direction, this means that you exchange some momentum with the atoms here. So any photon that come here leaves some information here. If 2 photons come here, they were emitted independently. They leave 2 independent informations in the sample. If 3 photons come out, they leave 3 independent situations. So this kind of very simple process will generate in first order states like this, okay? So what can be done from here, from there? Then you can come with a read field that basically will bring this state, this atom, back to the initial state. Once the second field do that, knows that your final state is the same as the initial state. Every time that you have that, you have what is called a parametric process. Parametric process, once you close it, the cycle, you have a very large enhancement. Because if you come back to the initial state, you don't know which atom did this process. Since you don't know which atom did this process, the probability to do this goes with n squared, with the number of atoms squared, okay? So basically, this is the same enhancement that you get basically with any of the strong nonlinear process. The strong nonlinear process are like cyclone harmonic generation, parametric down conversion, or 4-wave mixing, 6-wave mixing, and so on. All of these processes, they are enhanced due to parametric condition. Okay, so you use this here. And then with the reading process, what you are doing is just mapping the state of the ensemble into the state of a second photon, and that's how you end up with the entanglement. Here you have entanglement between a photon and the atomic system. You end up between the entanglement between 2 photons, or between 2 light fields. That's better to phrase. Okay? In practice, you use a configuration like this. As I mentioned, we are talking about a parametric process, so it's good to follow the guidelines of nonlinear optics. So this is a process, this configuration is called 4-wave mixing. You see that the right field comes from one direction, the read field comes from the other directions, and the photons also, they are opposite to each other. You see that this configuration, you have perfect momentum and energy conservation. And then you end up with all the information in the photons that are emitted from the ensemble. You don't leave any information inside the ensemble. This is also very important for quantum information, okay? Quantum information is all about information. And then if you leave information in the ensemble, then this means probably you won't be able to retrieve it. It's very different from the cavity QED system where you can always interrogate the atoms at a certain point, and then you can go back to the atoms. But for the ensembles, it's more tricky to retrieve any information that you leave there. But with this parametric process, yeah, what happens is that the system really likes to come back to the initial state and emit all information out to the photons, okay? And that's how we access this information. Okay, so let's define these two quantities. PC is the probability of getting one detection in two once you detect one photon in one, and QC is the probability of having this photon in the output of the ensemble. What this means, what's the difference here, is that one thing is you get a click here, what's the probability of get a click here? And the other thing is, once you know the losses in this channel, you can infer what was actually the probability to extract the photon from the ensemble once you prepare this collective state. Note, to prepare the collective state, that's a completely spontaneous process, okay? And since it's a spontaneous process, the probability is very low. The photon can go anywhere in space. We are just looking in a particular cylinder, but actually, you have fluorescence everywhere. So you can imagine that if you just put another fibers and look for other cylinders, it's just generate other collective states in different directions. But I chose to look just in one direction, okay? So once a photon is emitted in that direction, then I know a certain collective states in the system, and then the second photon should be emitted with high probability once the first was detected. So typical number is around, PC around 10%, 12%, and this QC around 50%. So it's a high probability, okay? And how can I characterize this kind of process? How can I know that I succeeded? Then I have to look at the characterization of the quantum correlations in these photon pairs, okay? And to do that, then we are going to measure the probabilities to detect clicks in one of the fields, field 1 or field 2. So I can have, for example, coincidence in field 1, that's this P11, or I can have coincidence in field 2, this would be P22, or some cross-correlation here, a click in 1 and 2, and this would give me this P12, or singles. I can have the probability to just get one click in 1, or one click in 2. This would be the P1 and P2. From these probabilities, I can build these normalized correlation functions. G11 is just that the G2 from the first lecture, my first lecture today, that's the probability to get a coincidence normalized by the square of the probability of getting singles. The probability to get a single square is just, it gives you the probability to have an accidental coincidence, okay? And P11 is the one that's really where you can have some non-trivial behavior. This is the probability of coincidence. For single photons, this should be 0 in principle, okay? You shouldn't have coincidence if you have single photons. But this is an ensemble. We have 100,000 atoms contribute to the process, okay? So it's not, you not get one easily. But for the G22, G22 is the same thing, but for the other field, this is autocorrelation functions, and G12 is the cross-correlation functions. That's the probability to get then a coincidence, one for each photon. Okay, so from there, you can deduce this non-classical inequality. I mean, for classical fields, you should have the square of the cross-correlation functions should be smaller than the product of the normalized autocorrelation functions. This is an old result by Clauser in the 1970s. This is from the time where the people were measuring the first quantum correlations. So that kind of measurement was designed to basically get almost nothing of correlation and tells if there is something or not, okay? So that's always a good point to start because that's a very robust measure. And I think that's at least the most robust that I know. I mean, you can get quantum correlations from this kind of analysis, I mean, much before you can get, for example, Bell inequalities violations, okay? For our particular system, if you don't look, if you just look for one field, like you look for these autocorrelation functions, actually, you should have a thermal statistics. What I just described here, I mean, if you excite a sample of emitters, let's approximate by two-level atoms. And then you put a detector here. Let's say that you don't put one detector. You put like a beam splitter and two detectors. This is called a Hamburg-Brown twist apparatus, okay? And you will find the calculations in many textbooks for quantum optics. If you have this ensemble of emitters, and then you calculate what's the autocorrelation function for this kind of systems, you get two for it. This is called bunching, okay? If you have a laser field, you should have one. And this is a very particular property of laser systems that you don't have intensity correlations in a laser system. So the photons that you detect are not correlated with the other photons that you detect from the laser. But if you have just an ensemble of emitters, you should have correlations, okay? And this is a classical correlation, this bunching. So if you have one photon, there is a larger probability that you get another photon close by, okay? But this kind of restriction leads to in practice, that this cross-correlation function, once it's larger than 2, then typically is a good sign for non-classical behavior, even though we are going to always measure all these quantities to check for this inequality. Okay, then that's a measurement in this system. Just to give an example, this P1 is the probability that you excite, you get excite the photon. Let's see, this is a function of the writing power. So what you do here is that you just decrease the writing power and then decrease the probability to generate the first photon. And what happened here is that your cross-correlation function goes up, 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 up. Okay, the maximum that I got was, up to now, was around 600. For parametric down conversion, you can measure the same thing. You can get these hundreds of thousands very easily in parametric down conversion, okay? But in atomic system, I can be close to resonance, and I can generate a lot of photons if I want. And what happens is that, you see, the state is approximately, it's proportional to 0, 0, plus square root of 1, 1, plus P 2, 2, and so on. If I increase the write power, it means that I'm increasing P. And then, once I increase P, I increase the higher order components, okay? This kind of states, a two-mode squeeze state, it's always entangled, okay? So you use it, for example, for optical parametric oscillators. You can use OPOs. They have also a very nice quantum properties. This is the same state, but is in the large excitation regime. Okay? So it's not a problem that your system is not quantum anymore. It's just because that inequality, the Cauchy-Schwarz inequality, that Clauser paper, it was designed to measure correlations in the single photon level, basically. It's the same thing for measuring Bell inequalities, for the discrete variables Bell inequalities, because then you are restricted to analyze the system at the single photon level as well. If you increase the probability of generating other photons, your measure of quantum correlations doesn't work anymore. It's not a problem with your state. It's a problem with your measure. So that's what you're seeing here, okay? If you increase the power, then you see the cross correlation goes down and eventually goes down below 2. 2 is here, okay? But if you decrease P, the right power, then you end up with a lot of vacuum, okay? And just a little bit of this component. And that's where you get these very strong correlations here. That's the same thing that you get from parametric down conversion with a crystal. It's just that in the crystal, it's very hard to have these other components. So you basically start here, okay? you start here. You have a very hard time. You have to work a lot with high power lasers to be able to put this down. Okay? And so the first measurement of this, so here we measured in 2006, we were measuring 600 here. The first measurement in 2003 was like 2.3, okay? But it was with a good resolution, it was quantum correlations. But then in 3 years, we were really able to improve by a lot. So at this point, what I mentioned is that, okay, you have parametric down conversion that you can generate this state. Or you can use this process, which requires, in these first experiments at least, a magneto-optical trap. So it's a much more complex system. So, I mean, if you're just interested in this state, it looks like, okay, you can work with parametric down conversion. You don't need this kind of process. But the difference here is that you can have storage. So we do need to increase the storage time in the system. And to do that, so you have to work. And it's basically a pathway similar to what I described in the morning in the cavity QED systems. You have to work to increase your coherence time. You have the same problem here. It's just that your first villain is different. So your main problem initially is the magnetic field of the trap itself. So in order to have a magneto-optical trap, you need a quadrupole magnetic field. A quadrupole magnetic field means that you need an inhomogeneous field in the MOT so that you can really trap anything there. But if you have an inhomogeneous field, it means that the field is different in every point of your trap. So each atom actually sees a different field. And when you deal with collective states, you mean that you have one atom that's in level S and the other in level G, but you have n atoms can be in level S. This means that if you start at time 0 in this state, and over time, all atoms sees a different magnetic field, and then they have a different dislocation of their Zeeman levels, you end up in a situation in which each atom processes with a different phase, with their state in a different phase. This is not a global phase. It's different for each atom. Okay? And over time, they will basically point in different directions. And so, after a while, these states will be very different from this initial state, and the superposition goes to 0, and all quantum correlations goes to 0 as well. Just to give an idea, that's for the storage time. In the first experiment, 2003, the storage time was really low. I mean, probably below 100 nanoseconds, okay? But that was with the magnetic field of the trap on. If you turn off the magnetic field of the trap, it immediately goes to tens of microseconds. Typically, for this system, around 20 microseconds, okay? And so this is always a big impact. For the line of work that I'm going to discuss here, we are going to use just this turning off the magnetic field for storage time, but actually this can be improved using other techniques, using dipole traps or many techniques in atomic physics that are known, for example, for ultra-cold gases. I think you are going to enter in ultra-cold gas this week, and then you are going to learn other techniques to increase the coherence time for much longer than 20 microseconds. But 20 microseconds already was enough to start work with this kind of system. Just an example, I mean, that was in 2005, something like this. Here in 2008, you already had 2 groups here that were already in the milliseconds range. And using, as I mentioned, more sophisticated atomic traps, using optical lattice or using magnetic field-insensitive states. Okay? So they got memory lifetime between 1 and 6 milliseconds. Okay? This kind of system, that's the same thing as we were discussing in cavity QED. These atomic systems, they are also the atomic clocks. So you expect that you can get long coherence times. It's just that you have to work a lot for that. I mean, so sometimes, so we want to explore one of the systems to do a task in quantum technology, and then you know how to do the quantum technology test, but then you have to learn all the techniques that the people from the clock community knows how to do, so you can you can be able to use that kind of coherence time. So that's more or less the point here. I mean, once you know what to do, you can use different techniques that are well known to increase this coherence time. And this is important, I will show here. So, okay, another thing that you can do, so what I mentioned here, I mentioned number correlations, okay? I didn't mention yet polarization, but actually this system, you have also correlations in the polarization. You can use the whole Zeeman structure of your levels, and then you can, for example, excite the system with a sigma plus polarization, and the emission, you can have emission sigma plus or sigma minus, okay? And actually, since if I don't prepare the initial state, I actually have an initial distribution of atoms in the Zeeman levels, and this will map to a different distribution of atoms in the final levels. The final level, I mean, the final levels here is sigma minus or sigma plus. They don't need to be equal, but they need to be really two different distributions from one side and the other. The important thing here is that once you detect one of the field in a way that you don't know, I mean, you can detect in this base, the circular base, and then you certainly know what's the MF of this last emission, I mean, inside this distribution. Or you can, but if you measure, for example, a linear base, and you don't know which one of the circular polarization the photon had, then you have also a coherent superposition here in the MF. What this means is that if you do the same process, but you use circular polarization in the right, and the opposite circular polarization in the read, in the output you have this coherent superposition between sigma circular, positive circular, and negative circular, and then you can map this with this quarter wave plate. You can map these photons back, okay, to the linear polarization, and actually you can measure Bell inequalities here. Okay, I will not enter in the details, okay, about Bell inequalities, just doesn't have enough time for that. But you can measure, once you have these entangled states in the Bell basis and in polarization, you have specific procedures that you can do to check. This is called the CHSH Bell inequality. You can measure this S parameter, and you can check if it's above 2, for example. And here's, as I mentioned, I can tune the cross-correlation function from going to really a situation where you don't have much quantum correlations up to very high correlations, around 100 here. You see that I need a G2 that's actually almost close to 10 to be able to violate a Bell inequality here. So that Cauchy-Schwarz inequality, you detected like weaker correlations than you can detect with this kind of Bell inequality. Okay. It's also a different degree of freedom. When you are looking for Cauchy-Schwarz inequality, you are looking for number correlations. When you are looking for the Bell, this kind of Bell inequality, we're looking for polarization correlations. And then, but you can have really a very good violation, really close to the maximum here. And you can also see how this, once you get this very good correlation, how it changes over time. So we can see the storage times also in these Bell inequalities, okay? And this is important because, I mean, if you can do Bell inequality, you already can do quantum cryptography here in the system. This is one of the degrees of freedom that you can use. You cannot do a quantum cryptography, for example, with this state alone, okay? If you just have number correlations, that's not enough degrees of freedom to really encode a key to do cryptography. But already with polarization entanglement, you can already do that, okay? Okay, but another thing that we can do is to generate single photons. So this is not exactly, this was not proposed in the original protocol, okay? The original protocol, you have this process, but this process was used since the start just to generate entanglement between distant ensembles. And from that point on, the focus is long-distance communication. However, if you have this kind of state in the system, you can always generate single photons. That's how you do single photons with parametric down conversion. Okay? And so the idea is the same. Every time you have these photon pairs, if you detect one of the photons, then actually what happens here is that you throw out this vacuum component, okay? And you are left with this single photon component here with some noise that comes with the higher order components. Okay? And so we are in this configuration. This was the first done in 2004, right after the first success demonstration of the generation of this state. For the optimization of the system, I mean, the optimal situation that I got, I mean, so we get a click here, and then I can check. So to know that you have a single photon, again, we go check for the coincidence here. Okay, so let's just move back a little bit. So I obtain a click in the first photon, and then I go to the read process and extract the photon, and then this extracted photon goes to a pair of beam splitter, and I check the probability of getting coincidence. And that's what I get. One here means that is what we should get for a coherent state, okay? And once this cross-correlation function goes up, that goes really down, and you can get down up to 0.7%. So it's 0.007 of what you should get if you had a coherent state. At the time, that's already a long time ago. At the time, it was compatible with the best single photon source then. Nowadays, nanometers can get better than that, okay? But any parametric down conversion system, you can also get something probably as good as this. You just need to know, I mean, you just need to have a use for that, okay? Because once you can get, you see that to get this pure state in all ensemble systems, and when I say ensemble system, I mean, it can be an ensemble of atoms, like here in the magnetic optical trap, or it can be an ensemble of atoms in a nonlinear crystal, okay? A nonlinear crystal is also an ensemble of atoms. Every time that you have an ensemble of atoms scattering the photon, the way to get to this kind of single photon regime is to reduce the probability of success. So as your system gets more pure, your life gets much worse, okay? It gets everything gets less efficient, everything gets worse. So that's a really bad trade-off, but you get a simplified system on one side, but you have this painful behavior on the other. Okay, but once you start to have storage, then you are able to do some tricks, okay? You can really use this storage to do something. And the first thing is to enhance the probability. I mean, you can turn this probabilistic source, okay? So you have a small probability to generate in a collective state, and then you have high probability that once this state was created, you have a high probability to emit the photon. You can use that, okay, to actually increase the probability to generate photon at a certain time. So you can create a pseudo-deterministic source. And how can you do that? Okay, so you see here the read pulse. You can say that I'm going to send a read pulse at a certain time. What I can do if I have enough storage time is that I can start to prepare the systems much before. I can start a sequence of writing and cleaning pulse. Write means I try to generate the state. I don't succeed. Then I send a pulse just to clean the system. And then I try again. And then I clean. And then I try again. And then I clean. Until I succeed. Once I succeed, then I don't send the cleaning pulse. And I wait for the read pulse. And then I extract the read pulse there. So this basically enhances the probability to generate a photon here proportionally to the coherence time you have. If you have like an infinite coherence time, your probability is 1, okay? So you have more or less a pathway. You can map, okay? That's always the trade-off in the system. You can always map memory time into efficiency. That's the advantage of having a system that's probabilistic but have memory. That if you have enough memory time, your probabilistic system can always result in something that is almost deterministic. So that was probably the first, one of the first applications. I'll show another one soon. Is this just to enhance the probability to emit a single photon? But actually, the first one was a little bit earlier than that, is that when we use this process to actually increase the efficiency to synchronize two different memories, okay? So the setup here is a bit more complex. So now I'm dealing with two different magneto-optical traps, okay? So this is two optical tables, and one optical table has a magneto-optical trap of cesium, the other also magneto-optical trap of cesium. And now I come with the right field, and the right field I divide in two different pathways. And each pathway I pass through an intensity modulator, an independent intensity modulator, okay? And after this intensity modulator, the right field goes to the atomic ensemble. And then I have this control electronics that's basically triggered by detectors in each of these traps. Okay, so if I detect a field one emitted in one of the traps, what I can do is that I can turn off this intensity modulator and I just store this excitation, okay? And then I can wait for the next one to be excited as well. And then once both of them are excited, so I release the read field to read both of them simultaneously, okay? And with this, okay, so the resolution is not very good here, but this just gives you the probability to get the 4 photons, 2 photons on the writing. Oh, here is escrita in Portuguese, but it's writing, and this is reading. So this is the writing stage. So the 2 photons in the writing stage and 2 photons in the reading stage. So this is a 4-fold coincidence whose probability is very low, okay? But once I have memory, the more I can wait for this 2 process to be synchronized, I mean, for the 2 memories to be created, to be stored together, the more I can wait, the larger I get for this 4-fold coincidence, okay? In the ideal case, I should have this green line here. In practice, you see that as I increase the number of trials that I can wait, once I prepare one memory, the number of trials that I can wait for the other one, you'll see this decrease. This comes from the coherence time, okay? And then it's getting harder and harder to take the stored excitation out of the ensemble just because I'm losing the collective state. But I can still have a large enhancement. For this case specifically, I have a 20-fold increase in this coincidence probability. In the next slide, I'll show the results of what I call a Hongo-Mandel experiment. You see here, when I read the 2 photons, I take the 2 photons to a beam splitter, and I try to measure the coincidence. If you have the interference here, if the 2 photons are indistinguishable, the interference here should result in no coincidence. Okay, this is the Hongo-Mandel interference. I will discuss a little bit in the next slide. But the important thing is the 20-fold. So the experiment that I'm going to show the results, it took 1 day to take the data. So if it didn't have this enhancement, it would be in 1 month. That's the difference, okay? So it's really, everything's really about increasing efficiency in the end. So as I mentioned, what we call this Hongo-Mandel, as I already mentioned, it's just the fact that when you get 2 photons with the same polarization arrive in a beam splitter, and then this is how they transform in the beam splitter. I already showed this earlier. But when the 2 arrive simultaneously, in the end, or you have the 2 photons in one port, the output port, or in the other output port, and vice versa. The only way that you have coincidence here should be if you have different polarizations for the 2 photons, okay? And so that's a very basic process. It's actually a function of the indistinguishability of the photons. So for that experiment that I just described, that's a 2006 experiment. So you have these 2 independent sources of single photons. So these are 2 magneto-optical traps, 2 different clouds. And what you get here is that if you have parallel polarizations for the 2 photons, you have this amount of coincidence. If you have perpendicular polarizations, you have this amount, okay? And you see that you still have some coincidence. This is really a function of this quantity here. is this two-photon component here. This two-photon component is enough to explain this residual coincidence here, okay? But we still have a larger reduction here, and so we have a lot of indistinguishability. If you want to improve this reduction, we really need to decrease the probability to generate the first photon, okay? And the other interesting is that when you look at this, you see, since this comes from just from this two-photon component, this basically means that the photons are very indistinguishable, because it means that they have the same transversal mode. That's easy part, because that's just, you can just put in an optical fiber, and then the optical fiber will really just filter out the spatial mode, and then this guarantees a good overlap in the spatial transversal mode. But then the longitudinal direction, then that's the time, then you need to have the same wave packet. And that's what we are showing here. You see this 2L, it means that it came from the L ensemble, the left ensemble. 2R, it means that photon 2 came from the right ensemble. The wave packet from the 2L and 2R can be very similar to each other. You see? The lines here, the solid line and the dashed line, they're just the unconditional photons. But once you condition with the first photon, you get the same wave packet. And once you fix the right frequency is the same for the two ensembles, the central frequency is the same also for the photons. So what's the moral here is that for such atomic system, you can really get indistinguishable single photons quite well. That's the kind of thing that's hard to get from a nanometer still nowadays, okay? But for these atomic systems, for an ensemble, the same as in cavity QED, you can get really nice indistinguishable single photons. And the interest for this is the same as for nanometers. I mean, if you have indistinguishable single photons, you can always try to go in the direction of do some kind of computation with photons. But here, you can actually synchronize your single photon sources. Looks like in the nanometers, you need to have many photons from the same emitter, and then you just delay the different photons to enter in the circuit with all of them, and then you have indistinguishability between these photons. But with this kind of atomic system, you can actually synchronize the source and then read them all together. This is just saying that what else can you do? This is a work now from my group here in Recife, the work of 2018. Is a bit straightforward. You can do also, you can create actual other Fock states, because actually it's easier to go to this direction here. You have a two-mode squeezed vacuum like this, what I wrote here in the board. You can do this process I just described, and then you generate this state. Once you get a first click in the right field, this is the atomic state, okay? Or you can just wait until you get 2 clicks, okay? The 2 clicks, then you can actually store this other state. You throw out the vacuum, you throw out the single photon component, and you store the 2 photon component, okay? And when you read out, then you can read out just a single photon here, or just a state with 2 photons in the same mode, okay? So that's a way that you can prepare a different quantum states of light. Also, in a way that you can store and then you can synchronize different systems. So this is just to highlight the flexibility that you have. You can generate this kind of state, and you can store and then you can use. And the same goes for the next step, okay? Now, finally, we go back to the protocol, the original protocol. Everything that is important is to entangle distant memories, okay? So what's the idea? The idea is to start with the process I just described. I mean, you come to a right field, and then you have an atomic ensemble, and then that field one, a right pulse, and then the field one is emitted. And then you have an entanglement between the atomic system and the field one. And then you come with another ensemble, and you do the same. You look at the previous experiment that I just described, This field 1 went to one detector, the other field 1 went to another detector, and they were independent. Now I can get this 2 field 1 and go to a beam splitter, okay? And after this beam splitter, then I put these 2 detectors, and if I have indistinguishability, and I detect, for example, a click here, in the end, I know that 1 photon was detected. It means that 1 atom was transferred. But the problem now is where, okay? You can have the atom transfer here, or you can have the atom transfer there. And then you end up with this entangled state, okay? You don't know in which place your atom is, single atom, okay? And these end up entangled, these 2 ensembles, okay? So you end up with entangled state of a single excitation, so you have 1 excitation in ensemble L and 0 in R, or vice versa, okay? When this was done, so we used 100,000 cesium atoms, the ensemble 3 millimeter long. This is the ensemble that I described before, but just the new details, just this was like 3 meters apart. This was important for the first experiment because actually the problem, I mean, is not really to entangle these 2. Huh? I mean, to entangle, what we are doing is just this. That's operationally, I come to a right field, I split this right field in a beam splitter, I excite the samples, you generate this field 1, and then it goes into fibers, another beam splitter, 2 detectors, and have some data acquisition, okay? And that's what you get in the ideal case. But the problem with this ideal case is that ideally you still have a phase that is arbitrary, okay? And in principle, you can have some phase shift here that you can include maybe to change this at will if you want. So the tricky thing here is that in the ideal case, you don't really control this phase, okay? And this phase here can be just a path length difference, okay? It can be just a mirror that is shaking, and your state can be shaking as well. And if this shakes, these nice entangled states transform in a separate density matrix really quickly, okay? And so we were able to store this entanglement for 1 microsecond, but we really had to work with that. You see, what we had to do, we had to inject light here at 1064 nanometer wavelength, and actually we had to take this light here close to the detectors, and we had to measure the phase of the interference of this in this wavelength, and actually tune the phase shift to keep this phase in place. Basically, we had to active lock the phase between these 2 pathways. So this is a huge, around 12 meters interferometer that we had to active phase lock if we want to stabilize this phase here and still see a nice entangled state, okay? But to generate this state, we just did a click, okay? The process that I described to you is in some ways trivial, okay? You just put a beam split, got a click, I have an entangled state. So the hard part is to show that you have an entangled state, okay? So you need to do that locking of the large interferometer in order to be able to verify your entangled state. And to do that, actually, we have these entangled states in the atomic system. What we do is that we read them simultaneously, and then we map these entangled states into an entangled states of the field 2, and that's what we infer. We do a quantum tomography of the density matrix of these fields that are emitted by the 2 different ensembles. So actually, the idea is to consider like this as a black box, and then you emit 2 different fields. How can I characterize the entanglement between these 2 fields that comes from 2 holes of this black box? Okay. And the idea is, so we are going to restrict the analysis up to 1 photon in each field, and one part of the theoretical problem here is to show that when you do this restriction, you can only decrease the amount of entanglement that you have, okay? So we need to have a robust measure. You need a measure that will not increase once you throw away information, okay? That's just a bad measure. But in this way, when we throw away this, for example, these elements of your density matrix, then the density matrix, the quantity of entanglement can just go down. But the ones that we can actually access experimenters is just the main diagonal and these cross terms here that will give some interference between the two pathways, okay? And that's what we do. We do some photon statistics. We see the probability to get 0 photon here and here, or 0 photon here, 1 here, or 1 here, 0 here, or 1 here and 1 here. And we can also take these two fields to a beam splitter, to another beam splitter, and then we see a visibility fringe here. Okay, so we have interference in these fields. And once you have this interference, then we can measure these out-of-diagonal elements. With these out-of-diagonal elements, then we can measure concurrence, this quantity here, which is a measure of entanglement, is a quantifier of entanglement for these bipartite systems. Bipartite system of qubits. So this is another point for characterizing entanglement. So I mentioned Cauchy-Schwarz inequality. I mentioned also a Bell inequality. Bell inequality is a witness, an entanglement witness. So once you measure it, you know that it has entanglement, but you are not saying exactly what's the quantity of entanglement. Concurrence is a quantifier, really, and it says how much entanglement you have to use in different tasks. And what we have here is a small quantity, okay, 10 to the minus 3, but since it's above 0, this means that they are entangled. You have to be careful about these quantifiers, because this quantifier is quite small, but that's for the state that you create, really, in the end. I mean, once you finish the writing process, the state that you have in the ensemble, you have some entanglement, and this state you map to the photons, and you measure in the photons. The state in the ensemble should have a larger entanglement than this, but not much larger. But this is a function of your writing process, okay? If you try to measure this, for example, using in parametric down conversion, you also have this kind of numbers here, because this takes into account vacuum, okay? So if I have a vacuum here, I have a P00 that's large. If I have a P00 that's large, these numbers go down. So if you have a parametric down conversion system that you can violate a Bell inequality at maximum, you can have a concurrence that is like 10 to the minus 4, 10 to the minus 5, just because that's the probability of getting a photon there, okay? And so it's really a quantifier of physical resource. So if you don't have, your resource is not deterministic, if you have something that's probabilistic, this is going to be in this quantity, okay? Okay, and so we have, I already called this attention. I mean, the atomic state should have a larger entanglement than in the fields, just because the readout procedure is a local procedure. All local procedures that can only act to decrease entanglement. And actually, this is a function, as I mentioned, of all the instabilities and deficiencies in the process. A couple of years, this was in 2005. A couple of years later, in 2007, you see that they grouped there in Caltech, they redid this kind of experiment, but instead of using ensembles that were separated by 3 meters, they used ensembles that were in the same cloud, separated by maybe 1 millimeter, okay? And just to generate this state, okay? So they could generate this state really very close together. So this is also useful. You need to think about, for example, for ion trap, or for the cavity QED with the 2 atoms, they are like micrometers apart, okay? But it's still interesting to know that they are in an entangled state, okay? So they are a millimeter apart. But it's not for quantum communication, but it's interesting for the control of the quantum state, particular quantum state. And then if you do this, much more control, then you can build interferometers that are really robust. You don't need to do active phase lock of the interferometers. It's really just passive stabilization. So it's really much easier to work with. then your C, instead of being 10 to the minus 3, it starts to be 10%, for example. Okay, so it can grow considerably. This is just an example. Later, they did also use 4 ensembles in a single trap, just to show that you can generate even more complex entangled states in a single atomic cloud. Nowadays, I think the record for addressing different positions of a cloud is around 255. I think there is a Chinese group that actually led by Duan, which was one of the proposals of this protocol. And he showed that actually you can address different positions of the cloud, and you have quantum correlations. It didn't address like this. This is really an entangled state between the 4 regions of the same cloud. When they address more than 200 different regions, they just show that you can address differently, but they didn't entangle all of them, okay? In this case, they had to characterize entanglement. As the system gets larger, it's much harder to characterize entanglement in the system as well. So you end up in this multipartite entanglement situation. We are getting close to, maybe the time is 5:30, that's right. Maybe we should use some time for questions. That time. I can continue from here tomorrow. It's 6 hours? No. 6 minutes. Okay, so we can stop here, and I can continue from here. The end of this talk, I can discuss. I can just comment before I pass for the questions. Is that this experiment is a connection between 2 systems. I mean, we succeeded in 2005, and the theoretical proposal was in 2001, so it took 4 years. So the development was much faster, just because the experimental system was much simpler. So that was the importance of that theoretical proposal. Once you can do this with a simpler system, then the experimental pathway gets faster. But okay, so we can continue tomorrow with the other parts, but now we have questions for this part. Okay, go ahead. Oh, let's see.
Thank you. I have a question related to the coherence of the in several slides before you were talking about the lifetime of coherence and how this time of coherence is important to store information. I would like to maybe get
you mean this
better idea.
Let's see if I can get there.
Yeah, maybe in some of
it's
one of those
here.
slides.
This part here for the coherence?
Yeah,
yeah.
Over the coherence.
Yeah, so
the lifetime.
The thing is, I think it's better even to go here. So when I have one here in the atomic part, okay, so I have one photon out, and then you can have the atomic part here before the readout process. Okay? This 1A here actually is this state. Okay? So if you have this decoherence, then actually this state will evolve with different phases for different atoms. And when you try to do the projection of this state at a later time with the initial state, then that's what goes to 0. So in the end, it's like if this amplitude probability is going to 0, because you're not able to read out the state. And effectively, then you lose the information. You think about, like, to do the DLCZ protocol, you have to entangle these 2 ensembles, and then you have to hold this state to entangle this other pair here. But if you have this decoherence, you cannot wait much before you disappear with this state. So you cannot do the protocol itself. That's
okay. I understand. And I have a question. I don't get it, the idea of how you measure the lifetime of that coherence. Experimentally, how you measure that time in the net
For
graph.
this one,
Yeah,
no, experiment, what you measure is that you measure the decrease the probability to extract
okay.
the photon. So
Okay.
actually, you are measuring this, it's like you are measuring exactly this process, because once you try to read out, the readout will map this state into another photon, but this mapping will only be effective if you do have this collective state. So you have this collective enhancement behind this process. So the first photon that's emitted, that's generate this state, this is spontaneous. You don't control when this is going to happen. But after you create this state, when you read this out, since they have the same phase here, they will interfere constructively to generate the second photon. If you lose this constructive interference, then you lose the probability to extract the second photon. That's the point.
Okay. And I have a question about the plot you showed us before, the next slide, I think it's the next
Before or
after, sorry.
after?
I don't know where is that plot. That storage time is
Okay.
what you
So you see here, this is a cross-correlation function.
yeah.
And this storage time means that I'm waiting this amount of time to come with the read field.
Okay.
And then if I come with a very short time with the read field, I can have this correlation. I can measure the G12, okay, at a certain time. And if I wait longer with the read process, then I cannot measure correlations anymore. And here it's just that after turning off the magnetic field, then if I get the read field, and then I just delay it this amount, I can still get a violation in the cross-correlation function.
Okay, thank you.
Okay. Is there any more questions?
Could I make another question?
Okay, go ahead.
Several slides after you talk about the entanglement between two atoms with the throughout the entanglement of the photons when you go throughout the interaction. I don't get it, the idea exactly of to have the entangled two atoms. Why I am interested in to have this entanglement between these two atoms.
You mean here?
Yeah.
Oh, okay, okay. Well, actually, this entanglement is what I'm representing here. You are me talking this one. Yeah. So when I write here this entangled state, that's the entangled state.
Yeah.
And this is a tricky question about why is this interesting. The thing is that if you have two systems like this, and you can do actually a Bell measurement here, you can do exactly that entanglement swap protocol. Note, there is some tricky issues here. You see that's 1001, so there is one excitation here, but you don't know where, okay? There is one excitation here, you don't know where. Once you do a click here, you get a click here, you don't know if you extract the information from here or from there. You see the trick? You can, if you do the Bell measurement here, and then you get just a single click, you are left with a single excitation, but you don't know in which ensemble. But it is a kind of entanglement that is more subtle, because it's an entanglement between one excitation and no excitation.
Okay, it's kind of a way of to obtain a bubble state between those systems, those two atoms. That I get the idea.
Okay, but these are not atoms really. This is a collective excitation in one system,
yeah,
and no collective excitation in the other, or vice versa.
Okay. Thank you.
Okay, but this is the the same kind of state that you get, for example, if you had a single photon, and then you reach a beam splitter with a single photon. And then it can go through one direction or the other, or the other way around. And then you have this kind of entanglement between one photon and no excitation in the other.
Yeah, like in a Mach Zehnder.
Yes, like in a Mach Zehnder.
Okay. Yeah. Thank you.
Okay. Okay, go ahead. Okay. There is one here. Oh, okay. Sorry.
In entangling with two atoms, I guess, you said that has a phase shifter. I guess some slides after. This.
Yes.
And this parameter eta, you said that can control this. Is used a mask of phase or something like this to control?
No, it's really just a PZT in a mirror. This is really an optical pathway difference. The problem is that this is an interferometric process. And since it's an interferometric process, it depends on the path length in one pathway or the other. Look, the problem is not that the path length is changing. It's just if they change relative to each other. So, I mean, we can send this light here, and then we can check if this light has the pathway fixed. So if you feel the pathway changing, then we can move back. So it's just a locking of the interference fringe. It's tricky, but it was doable. Actually, I mean, the original protocol was much cleverer than this. So the DRCZ protocol was not a protocol to create this state, okay? It was actually a protocol to create two pairs of parallel states. And that was the next stop that I'm going to discuss tomorrow. If you have two pairs of states, okay, then you can use the same optical fibers with different polarizations, okay? And actually, this system is much more stable than this. So actually, experimentally, it's easier to create these two pairs of states with fixed phase than to create that with active stabilization. So that's a detail, but of course, we only knew that after we did that. but basically, it's possible to do the experiment with two pairs in parallel with just passive stabilization. But to do, if you remove this one, because for this kind of system, in the end, you're not going to control this phase, but to do, for example, a Bell state measure, a Bell inequality measurement, in the end, you only need the difference phase between these two. And this was already in the original protocol, that in the end, you only need the stabilization of this. So actually, you can leave this phase just fluctuating, but if you have another ensemble that fluctuates together, then in the end, you can do Bell inequality violations and cryptography. So there is this subtlety, because this is a pain to do. But it's doable, it's not just not nice, but it's not necessary for the protocol in the end. Okay,
Okay, thank you.
Another question? No? No, so.
So, okay, so thank you. See you tomorrow.